Welcome to the Argument channel. This is the Real Analysis class, Lecture 5, Properties of Limits. So we looked at limits in the previous lecture. Now let's look at some properties of them. So let's see what it means for a sequence to be bounded. We say a sequence AN is bounded if you put all of the elements in that sequence into a set and that set itself is bounded. And that's it. Now, what this means is AN has a lower bound and an upper bound. So let's say L is less than or equal to AN, less than or equal to U as the upper bound, and L as the lower bound. Then AN itself is less than or equal to the max of the two. I'll just call it M. So let's use that definition in a proof. If AN has a limit L, then the sequence is bounded. Proof. Suppose AN goes to the limit L for epsilon equals 1. There exists n in N such that AN minus L less than 1 when N is greater than or equal to N, because we're assuming it has that limit L. So for any epsilon there would be an N, so let's just choose an epsilon equals 1 and use that N, big N. Therefore, using just by expanding that out, we have that negative 1 is less than AN minus L is less than 1. So negative 1 plus L is less than AN is less than 1 plus L. Now take M is equal to the min AN of A1, A2, all the way up to AN minus 1. So these are the ones that that don't satisfy this. So there's some in there that have that are greater than 1 or equal to 1. So now we want to show it's bounded, and M is equal to the max of A1, A2, all the way up to AN minus 1, and include 1 plus L. Whoops, looks like I missed one here. Plus L. Therefore, M is less than or equal to AN is less than or equal to M. So it has an upper bound and a lower bound for all n is a natural number. So an is bounded. And the trick with this proof is we assumed it had a limit, and then we found where it started converging at n for epsilon equals 1. Then we found a lower bound for the sequence by finding the minimum of a finite set. So 1 minus L is the minimum of an for all n greater than big N, and 1 plus L is the maximum for all n greater than or equal to n. So now we have these finite elements, a1 up to an minus 1, going n 1 plus L, so we take that max, and same, we can take that min. So we needed that because we can't take mins and max of infinite sets. And then we concluded that it was bounded for all n and n. So the set is bounded, so the sequence is bounded. Now let's look at an example. Take an equals sine of n, or even -1 of n, are bounded, but they do not converge. So the opposite isn't true. A bounded sequence does not always converge to a limit. For converse of above proposition, not true, i.e., that is, bounded does not imply convergence. So let's look at another application of this in a proof. Suppose an goes to L and b of n goes to m. The following properties hold true. A of n plus b of sub n goes to L plus m, so the sum of a sequence approaches the sum of the limits. If you multiply it by a scalar, then that will just approach the scalar multiplied by the limit. So that's for all alpha real. 3. If you multiply the terms of the sequence, then they approach the limits multiplied together. 4. If you divide them, then the limit will be the division of them as well. If bn is not 0 for all n, and m not equal to 0, just to keep everything nice. So we have these properties of limits. Let's prove a couple of them. So let's prove one. Suppose an goes to L and bn goes to m, as we said. We want to show that their sum approaches L plus m. So let's use the definition of the limit. So let epsilon greater than 0 and let n let me rephrase that. And let epsilon greater than 0, and since we know that the sequence an has a limit L, there's n1 in n such that an minus L is less than epsilon, and since b of n goes to m, there exists n2 natural such that b of n minus L absolute value is less than epsilon. So that's for all n greater than or equal to n1 for A, and for all n greater than or equal to n2 for B. Now, because epsilon is a positive number, epsilon over 2 is also a positive number, so there's also an n1 that satisfies it for this value and for this value. So the n1's now changed, but everything else remains the same. So choose n equals max n1, n2. Suppose n greater than or equal to n, we can now conclude an plus bn minus L plus m is equal to, if you just rearrange, an minus L and use a triangle inequality, bn minus m is less than epsilon over 2 plus epsilon over 2 is equal to epsilon. So an plus bn approaches L plus m. Now let's prove 3. So for that, that one said an times bn approaches Lm. So suppose an has limit L and bn has limit m. Since an goes to L, let me rewrite that, L, an bounded by the previous theorem, and we can then say there's a k such that an less than or equal to k for all k natural. So now let epsilon greater than 0, there's a n1 in the natural numbers such that n is greater than or equal to n1, implies an minus L is less than, we'll fill this in later, and also there's an n2 such that n greater than or equal to n2 implies bn cell is less than blank. We can put anything we want here as long as it's a positive number. It doesn't always have to be epsilon, because we can manipulate epsilon so that it works out nicely in the end, and that's what we're trying to do. So choose n as the max of n1, n2, and suppose n is greater than or equal to n. Now we put in the definition for the limit, and we want to show that this is less than epsilon. So an, bn, we add in a and m and subtract in a and m, so nothing really happened. Now we split the sum. Let's group terms first. So an whoa, that's ugly. An bn minus an m plus an m minus l m. So just to make the triangle inequality clear, and that is less than or equal to an bn minus an m. We're splitting it on that addition. An m minus lm. And that is just equal to an bn minus m. If we take an out of the absolute value, and what do we want? And if we take m out of this absolute value, then that is less than or equal to k bn minus l plus m an minus l. And then now let's choose these values because we want it to end up as less than epsilon in the end. So let's choose epsilon over 2m. That way this turns into an epsilon over 2, and choose epsilon over 2k. That way this turns into epsilon over 2. That way we have an epsilon at the end. So it's be less than epsilon over 2 plus epsilon over 2. If you make the substitutions for this and this, we have this inequality, and that's just equal to epsilon. So that completes the proof. An bn approaches lm, or has a limit lm. Okay, these are the properties of limits. Now let's move on to monotone convergence. So let's define what that means. We say a sequence is monotone increasing if an is less than or equal to an plus 1 for all n and n. So that means every next term in the sequence is greater than the previous term, or every previous term is less than the next term. I guess that's the way this inequality is supposed to be read. So, and a strictly monotone increasing sequence just gives it, changes that to a strict inequality. That's for all n a natural number. There's similar definitions for monotone decreasing. So just for completion's sake, let's just write it out. Monotone decreasing is if an is greater than or equal to an plus 1 for all n in n, and strictly monotone decreasing if an is greater than an plus 1. All this talk about monotonous makes me very self-conscious about the tone of my voice now. So just to plot that out, we have a the real line here, and the sequence will look like that. So this would be a monotone increasing sequence because the each successive term is less than or is greater than the previous term, and let's say it approaches m. So where m is the supremum of the set of everything in the sequence. So theorem. What do we say about monotone sequences? So this is called the monotone convergence theorem. Every monotone increasing sequence that is bounded above converges. And that's it. So you can see the power of this theorem. Instead of doing rigorous epsilon n proofs to show convergence, we can just show the sequence is a monotone increasing sequence, which is a bit easier to show. So proof. Before we prove it, just want to add that this holds for monotone decreasing as well. So let's write that one out. So if you just replace increasing with decreasing, and bounded above by bounded below, we have that. I won't actually prove this, we're just gonna assume it's true, just for the sake of moving on. Definition, we say an is monotone if it is monotone increasing or, whoops, don't want to underline that actually because that's all you'll find, or monotone decreasing. and that's just a side proof or a side definition. So it turns out we actually are proving it. I'm just following along with my notes. So we just had a definition in the middle. So suppose AN is monotone increasing and bounded above. We want to show that this sequence converges. So we know it's bounded above, so let L equals the supremum of the sequence. Note that supremum isn't really defined for sequences, so it's the supremum of the set of the elements of the sequence. Just a little technicality, which exists by the least upper bound property, which we looked at before, which said that anything bounded above has a supremum and it is unique. Least upper bound principle. Now, let epsilon greater than 0. Just so we're, it's not on the page anymore. So let's say we want to show AN converges. So that's why we have this epsilon here. L minus not epsilon is not an upper bound for A because it is the least upper bound. So there is an N natural such that AN is greater than L minus epsilon. So this implies AN goes to, oops, skipped a line there. For all n greater than or equal to n, L minus epsilon is less than AN, A of big N is less than or equal to AN is less than or equal to L. So what this means is negative epsilon is less than AN minus L, less than or equal to 0 less than epsilon, which means that AN minus L less than epsilon. Therefore, we have shown AN goes to L. Just so we're clear on what happened here, we stated that L minus epsilon is not an upper bound for AN. So that means at some point AN is greater than L minus epsilon. So for all n, greater than this point where it becomes less than, greater than L minus epsilon, we have L minus epsilon is less than AN, and that's less than or equal to everything after because it is monotone increasing. So this is from monotone increasing. And this last inequality is because it is an upper bound. And just so we associate this inequality with this one. So that's where that comes from. And then you subtract L from everywhere. And this gives you that line, and this 0 less than epsilon is just from definition of epsilon greater than 0, so 0 less than epsilon. So now that gives us what we want. Okay, so now let's prove the one for monotone decreasing. It's pretty much the same. So suppose Bn is monotone decreasing and bounded below let m equals inf of Bn. I won't write it again, that is because of the least upper bound principle, and let epsilon greater than 0. So L plus epsilon is not a lower bound for the sequence Bn. So at some point there's an n as a natural number such that it is going to be lower than L plus epsilon. So Bn B big N here less than L plus epsilon. That just made me realize the N there is different too. So N, just re-highlight that. And now we do the same thing. So for all n greater than or equal to n, we have that let's flip that last one. So Bn less than L plus epsilon is the same as L plus epsilon greater than B big N. And because it's a monotone decreasing sequence, we have that B of n is greater than or equal to B of n, because n is greater than or equal to n. Small n is greater than or equal to big N. So because of monotone decreasing, that's that. And that is greater than or equal to m, because m is a lower bound. So if we rewrite that and ignore the big N term, we have this. And subtracting epsilon, or subtracting, why do I have m's and l's? My bad. So that's an m. I have another L somewhere. No, looks like we're good. Subtracting m from every side, we have that epsilon is greater than Bn, is greater than or equal to m. Whoops, I didn't subtract it all. Bn minus m is greater than or equal to 0. And so I'm a bit unsure on how to proceed with this proof. Oh, I don't think we can show the absolute value is less than epsilon from where we are. So let's backtrack. So imagine none of those things were said. The sequence negative bn is monotone increasing and bounded above, because if we negate it, then we get that so negative b of n, let's ignore this m equals inf part, approaches some L from what we said above, where L is equal to the supremum of negative b n, what's the n equals n, and so that means that from a previous property, Bn approaches negative L, because Bn alpha negative Bn approaches alpha L, where alpha here equals -1. From the properties of limits, and we're done. Bn converges. So Bn converges. Okay, that's it for this lecture.